That's right. So we're gonna shave off a ton of time. Yeah, every exam that you write, instead of 3 hours, it's like you write your name, hand it in, I'm all done. Just took me a couple minutes. So we're looking at that instantaneous rate of change. When we graph all of those points that are on the tangent, we notice it makes a pattern. It makes another graph. If we take that pattern and look at it, we start to figure out how we can use this to do it quicker. So we did this just before. We used Newton's quotient. We found out that the derivative of this was a line, and we got y prime equals 2x. Pretty cool. Then we did this one with our graphing software, and imagine doing it with our Newton's quotient. These are still good to practice using your Newton's quotient, so you should do that. And we found out this one was 3x squared. And similarly, you could do x to the 4, and you could find out, use a different notation just to mix it up. You could get 4x cubed. And literally, that's how long it takes. You look at it, you write down the answer. That's how much faster this is going to be. So now the question is, how do we look at these, 4x cubed, 3x squared, and 2x, and describe a pattern that we notice? How did I notice the number in front? We already talked about noticing the power always went down by 1. Any ideas how we could get this number in front? Right? If I picked another one, you know, y equals x to the 8. It's going to be something x to the 7. Any guesses what the number in front would be? 8. Perfect. So a pattern occurs. What is that pattern? It's what we call the power rule. It allows us to do these derivatives much faster than the definition of the derivative. And sure enough, whatever your exponent is, so if I notice that my exponent is n, that n comes out in front. And then we also notice that our new power in our derivative is always 1 less than what we had before. And what's cool about this is we've only done it with whole numbers, with positive natural numbers. It's true for all rational numbers, even fractions. Okay? Now, just going to go back to one of the hardest questions. Remember doing this one? Okay? You remember doing this one with the definition of the derivative? We had to multiply by the conjugate in order to simplify it. It was a very complicated one because when we were using the definition of the derivative, we got stuck and didn't have any idea how to go from there. But because the power rule works for any rational exponent, we say to ourselves, I know square roots can be changed to x to the power of what? Half. Now, if that half comes out in front, what am I going to get? 3 halves. If I subtract if I subtract 1 from the exponent, how much faster was that than using Newton's quotient? Basically, we could just look at the answer. Notice our half came out in front. We're going to talk about how that constant in front doesn't make a difference. We're going to add that as a rule, and then we can quickly find the derivative. All right, so where were we? Power rule, these ones. So now we have x to the 7. The derivative will be, exponent comes out in front, 7x to the 6. Okay, I'll give you a 10-second head start, and you can do the next couple. When it's y equals, you can choose either y prime or dy dx as your notation. I will try to mix up notations just so you get used to all of them. Did you get 21x to the 20? Can you imagine trying to do this with Newton's quotient? X to the 21. In the expansion of x plus h to the 21, how many terms will there be? 22. And then you have to factor an h out of 21 of them just to cancel out your h's. Okay, yeah. So this is one of those rules that once you learn it, it's very hard to turn back. It's very hard to go back to your old methods of the definition of the derivative. Now, there's going to be times, like in this one, where you're going to have to take a little bit extra time before you do the derivative. Because the power rule worked when we had something x to the n. We don't have something x to the n here. We have 1 over that. But if we have an exponent rule that lets us change this to x to the something, that's going to help us. How could I write 1 over x cubed as x to the something? What power or exponent rule can I use? The negative one. Well, if I have x cubed on the bottom, that's the same as x to the minus 3. And now, I bring that minus 3 out in front. This is where you're going to make your mistake. Minus 3 minus 1 is minus 2? No, it's minus 4. And you will make that mistake. You will subtract the wrong way. Here's our square root one that we looked at before. Take a little bit of time to rewrite it. You wouldn't need the brackets there. They actually look ugly. Oh, much prettier. And now we can bring that half out in front. Subtract 1. Everybody okay with that? Got to think of common denominators, so you're going to get really good at subtracting 1 from fractions. Okay, our exponent rules combined here. First of all, cube root of x to the 4 becomes x to the 4 over 3. And now, take another step and say 1 over x to the 4 over 3 is the same as 1 over x to the negative 4 over 3. Once you've got it in this form, now we can do the derivative, the power rule. This negative 4/3 will come out in front. Subtract 1 from negative 4/3. Negative 7/3. Nice. So we have the note at the bottom saying that whenever you have a radical, you're going to change that to having a rational exponent so that you can solve for it.